High-impact, low-frequency events, such as extreme weather and natural disasters, can severely disrupt power distribution networks, threatening electricity supply continuity. The fear of large-scale blackouts underscores the need for coordinated restoration strategies to safeguard critical services. To address this challenge, ICCSNTUA presents a holistic post-disruption distribution system operation and restoration tool that leverages microgrid formation, optimal scheduling, repair crew dispatch, and sequential cold load pickup to enhance network resilience. The tool operates sequentially through 4 integrated optimal power flow-based models. First, it determines the optimal partitioning of the network into microgrids, aiming to maximize critical load coverage, constrained by available grid-forming assets. Next, it applies model predictive control-based scheduling of distributed energy resources to sustain at least the critical loads throughout the examined time horizon. Once microgrids are stabilized, the tool optimally dispatches repair crews and coordinates fault clearance and cold load pickup to restore the system to its normal operating state. The 125-bus Greek pilot distribution network, located in Xanthi, is selected to test and validate the practicality and application of the tool workflow. The execution of the tool is sequential, and the exported results are presented in a user-friendly graphical user interface. Before execution, network data must be collected through MATLAB and Excel input files, including the network's asset connections, load profiles, identification of critical and non-critical loads, faulted branches, and technical and cost parameters of distributed energy resources. The graphical user interface presents network topology, its assets, formed microgrids, and the percentage of the connected critical and non-critical loads. For this demonstration, both the primary substation and 13 randomly selected distribution branches are assumed to be de-energized following a catastrophic event. Initially, the microgrid formation module identifies which and how many microgrids can be formed, with the objective of maximizing load supply coverage across the network while prioritizing critical loads. This determination is constrained by the available grid-forming assets. In this demonstration, 4 grid-forming hydropower units are available, thus limiting the maximum number of microgrids to 4. Based on the network failure constraints, 3 microgrids are formed in this case, each displayed in a different color: blue, purple, and green. The user interface shows the nodes where the network assets are connected, including energy storage systems, photovoltaic power plants, and critical loads. The de-energized network is depicted in gray. The results indicate that these microgrids can supply around 90% of the critical load across the network. The end user can then execute the tool's second feature, which determines the model predictive control-based optimal scheduling of distributed energy resources within the formed microgrids throughout the examined time horizon, aiming to energize as many loads as possible. The results show that microgrids' demand is met by the available resources, and in some cases their capacity also enables battery charging. After the determination of microgrids and their operation, the tool decides the optimal transportation and repair sequences of repair crews with model predictive control to restore the faulted distribution network step by step. The user interface illustrates the sequence in which gray areas turn yellow, depicting the progressive re-energization of the grid. The repair sequence clears 13 distribution line faults and restores the system to its normal operating state within 439 minutes. Once a fault is cleared, previously de-energized areas can be energized, allowing frequency-constrained load pickups to reduce outage costs and support a smooth return to normal operation. Load pickup decisions provided by this module ensure compliance with safe frequency conditions, maintaining the rate of change of frequency nadir, and steady-state frequency within predefined limits. By integrating microgrid formation with advanced operational and restoration measures, this tool supports DSOs in reducing outage durations, minimizing service interruption costs, and improving system resilience against catastrophic events. It demonstrates how coordinated decision-making and dynamic network reconfiguration can transform post-disruption operations, enabling power systems to withstand and recover from severe damage more effectively.